So we are recording. So just a quick refresher on the topic we started on Monday. That is the topic of root finding methods. And one prime example where we might need a root finding method is in thermodynamics. So if I count my gases as ideal, everything is nice and easy to calculate. And we know that P times normalized volume is equal to pressure times normalized volume is equal to the constant gas constant R times temperature. So if you give me any two out of the P, V, and T, I'm going to give you the third one by a very easy calculation. So this is an example where we have a formula that gives us sort of a result we need based on whatever measurements we make. However, for the most part, if I'm in a reservoir at 3 kilometers of depth, my temperatures are high, they're somewhere around 100 Celsius degrees. My pressures or stresses that I'm under are high as well, somewhere on the order of 70 megapascals. Okay? So even if I'm a very nice fluid, it's very hard to imagine, or very simple gas, it's very hard to imagine that that gas will be sort of an ideal gas and behave ideally. And we know that hydrocarbons are very complex mixtures of both simple and very complicated gases and fluids within. So different components will behave differently and in a very complicated way. And for that, I need a little more realistic equation of state that relates pressure, temperature, and volume. And one of those is Peng-Robinson that is used a lot. Well, here, if I give you pressure of 50 bars and temperature of 473 K, okay, if I need to find the volume, it's not a simple calculation anymore, not the one that I can easily do by hand. And this is our motivation to do root finding methods. And how we're going to attack this mathematically or numerically is that we're going to, all of these problems, and they can be very different, we're going to pose in a form that f of whatever variable it is that I'm looking for is equal to 0. So basically I have to move around my variables, do some algebra, and present it in that form. And then we're going to find the root, or rather the VI in this case, that makes this equation 0. That's what root finding means. So all of the methods that we actually go over, and we're going to do about 5. We started with one last time. We'll have a way to attack f of x is equal to 0, or finding x where f of x is equal to 0. So that's one of the examples. Second one was also a falling parachutist. This is where I'm an engineer that is trying to optimize a parachute, and based on its shape, it's going to have a drag coefficient that I cannot necessarily easily just find what it is, given the shape. So what you do is you do a lot of testing where you can measure the velocities and everything. So from the force balance of a landing person, and I guess in the lab you wouldn't start testing this with a person, but with something that you can break. Whatever it is, you're going to measure velocities. You will know the mass of the thing, and you will do this balance, and you will find, based on the time and the velocity at the time of the measurement, you're going to find what your drag coefficient is. Okay? And you can basically run this test multiple times and look for what C is. So you have to kind of solve this multiple times for C, and possibly with slightly different coefficients all the time. And that's one example that we started working with in the class to actually find the root of this. So plain and simple, you have nothing else if you just have maybe a calculator. The quick thing to do is to take a number of values that seem realistic or in some sort of physical range of what drag coefficients should be. I know it shouldn't be minus 300 because drag coefficients are by definition positive. So let's start with something that is larger than 0. So basically you test a number of values and see how is your function doing Is it positive? Is it negative? Is it very small? Is it very large, right? So basically we want to we can tap around it and find where is it close to 0 and try to get closer to it. So you could just use your common sense to get closer to something that is there. But common sense is great when you're quickly doing something, but what works the best is actually have an algorithm that will kind of proceed and always give us a result and employ computers on the way. So one way, again, is just to take a bunch of values and see, oh, I'm first positive and then somehow I jump to negative values. Well, if I have a continuous function, not that all functions are continuous, right? But if I do have one, then I gotta cross 0 somewhere in between this 6 and -2. Right? So that's a basic theorem from mathematics. If I have continuous, and especially continuous differentiable, a continuously differentiable function, I will somewhere in between these two values cross a 0. Okay? And basically this is my starting, this interval is my starting point. If I just plotted this, which is another common sense thing to do, I can just kind of zoom in and see where the value is. But again, that's not efficient. I want that value and move on because my calculation is possibly, my flash calculation from thermodynamics is needed in my reservoir simulator, okay? To figure out how many phases do I have, 2 or 3, right? So basically, I need a value and then my workflow has to proceed based on that value. So just zooming in and looking how it looks like is nice, but it's not something that I need. Yes, question?
What would happen if we have multiple loops?
Great question. So we had that instance in our quiz assignment, didn't we? Okay. So I'm gonna address that in a moment. So basically what we did is one of these algorithms is basically saying, okay, give me an initial bracket where you think you have a root. Okay? That bracket, it's a positive times a negative value, therefore that multiplication has to give me a negative number. Then I'm going to bisect that bracket into half and see which half is still following this rule. Keep that half and keep going. So when do I stop? When I'm happy with how close I got to the root. I decide that, or if I'm using somebody else's solution, they decided it for me, so that goes sometimes into a black box of the algorithm, so certain small decisions. But basically, physically, it should make sense if your drag coefficients are typically under how sensitive is your problem to a drag coefficient. If a changing drag coefficient from 10 to 20 doesn't really change your solution too much, well then 0.1 is just fine, right? But if you're changing your drag coefficient between 10 and 10.1 makes a huge difference in how sensitive your problem is or solution or time of the fall and so forth is to it, then you need 10 to the minus 6, okay? So that's kind of relative to the problem that you're working with, where you're going to stop. But in a lot of cases, here in our, we're just going to take 10 to the minus 3 or 10 to the minus 6 and call it a good day and move on, okay? So you have to have some sort of stopping criterion. This is also a much larger point about any numerical iteration. So my numerical solutions, they typically iterate. They start from a point, so I have to initialize. Then they move through a loop, and hopefully they improve within that loop. And then I have to somehow tell it how to stop. Computer cannot just keep going. So there has to be a way to actually stop your algorithm and then your result is as close as it needs to be to your solution. All right. So this bisection is what we actually implemented. So basically, I keep bisecting the interval, testing whether that interval is still a bracket, and then moving on. So I'm just going to briefly go over the solution we came up with last time to review. So this is my code that I wrote last time. So first, I basically just plot the function on some range. So you have to give it the range. And sometimes whatever you give, it's a bit of a trial and error to see what range kind of works. And in this case, it appears that even over a large number of values, I really have only one root, so no problems with multiple roots, right? So I basically focus around this root. We started with 12 and 16 that we already saw in the slides. And basically, while the difference between these two is larger than whatever value I put in as a stopping criterion, then bisect this interval, find the midpoint, and then evaluate from midpoint to the upper end of the interval. Is this my new bracket? Is this rule for the bracket true? If it is, then move your lower end of the interval to that midpoint. So now my interval is smaller. And if not, if basically the other end is my bracket, then move upper part of the interval to that midpoint. And again, my interval just got twice smaller. Okay? And otherwise, okay, it seems that I've hit a jackpot and I should go play a lottery because somehow I managed with that midpoint to hit precisely the 0, because otherwise this thing is 0. It's not positive, it's not negative, it must be 0. Okay? So basically, I'll just shrink my interval to that one point, and that is it. And at the end, we print the result. And we see that when we evaluate that, we get somewhere around 14.78. We can formulate a function with the idea that every time I want to have a function is when I want to execute this multiple times. So I want to just call this block of the code with different input parameters and use them up. So you had an assignment for a cubic function to basically modify this and use this with a cubic function. Cubic function being cubic, a polynomial, is going to have up to 3 roots. Okay? So polynomial of order n is going to have up to n real roots. So basically, which one do I pick? It's on me. Okay, so I'm going to show you the solution that you should have gotten, and I hope you upload it to Canvas. But basically, again, this function was x to the cube minus 5x squared plus x plus 2.5 is what you got. So basically now I just changed my routines and I changed my function f, that's all I did. Okay? And then I need to plot, except that the range that I'm going to plot is going to be a little smaller. So when I plot it, I get something like this. So indeed, I have 3 roots. Now, if you plot it over a larger range, so if you did something like this, this is what I need, okay? Then it's kind of, you're like, what? What is this? Well, you obviously kind of need to chop this part. You're getting so positive up to 10 to the 8. Obviously, you're not going to get any zeros. If you think about it analytically, x to the cube is going to overtake, and it's going to be, for very large values of x, it's going to be very positive, so you're not going to find any roots here. Okay, this becomes the dominant part. So obviously, I can go lower. Right? So this is where you play with it a little until you can recognize something. Okay? And since I know that this is cubic function, I know I don't have more than 3. Okay? So this is it, these are the 3. And now you pick the one you want. Okay? So your bisection algorithm, you can surround yourself around this root that is close to minus 0.5, right? So minus 2, 0 would do as a bracket. Then another root is between 0 and 2. Okay? And another one between, well, you can do 4 and 6 or 2 and 6. Okay? You're going to get ever so slightly different solution, but it's going to be within whatever epsilon you gave it to as how close you need to get to the root. Did everybody successfully, semi-successfully complete this?
What if we took 3 roots?
So, okay, so that's a great question. What do you get if you get 3? So, obviously, if I take minus 2 and 8, okay, That is a bracket by definition of a bracket. This end is negative, this end is positive. Negative times positive is negative. So it passes my test of a bracket, it's just that it has 3 roots in between and not just 1. You're going to find one of them.
Yeah.
And which one, there's kind of no telling until you actually start the process. Okay? So that is, now, you might, in a very weird possible situation, is that you might not find the bracket as you zoom in if you have some other complex roots in there. So one such thing is, if you think about basic parabola, x squared, it has a double root at the 0, so it looks like this. Can you find the bracket? It's always positive. There's no bracket. Well, we're going to actually deal with some methods that can deal with that. Okay? But using bisection method, you cannot find 0 effectively because you can't even start. So f of x is equal to x squared is always positive. Okay? No bracket. Otherwise, I have to bracket one root. So that's what double, that's because x squared is double root. X times x, so I have 2 roots that are the same within. And that's a problem in root finding methods. And that's why root finding is not necessarily always straightforward. There's no one recipe. You kind of have to work with the function you got. Now, as an engineer, it's fine. Because often when you're actually doing a solution, you're going to do, for instance, thermodynamics, Peng-Robinson, in a specific reservoir, right? You actually still know. You know what your range of temperatures are. You know what your ranges of pressures are, right? So you work with those, and in those values, you will find the method that works with best for the problem that you have. And then you're going to model that, and you're going to implement that. And that's what you're executing from then on. Okay, so it's not all bad just because right now we don't know precisely what is the best method to work for all different problems. Okay, so let's actually give it a try here. I'm just going to try it for what happens if I do -2 and 8. Okay, and I'm going to comment these other 2. Whoa. And apparently I did not. Okay, so it seems that I'm going to zoom in on the one around 4.67 if I do -2 and 8.
You did that for the second one? The one.
So let's actually look at it a little. What will the method, because this is actually something that might come on a test. So if I start with -2 and 8, if I bisect the interval, what's the midpoint? -2 plus 8 is
3.
divided by 2 is 3. So 3 is right here. Okay. So if I evaluate now this end times this one end, I'm going to have negative value times a negative value. So this is not going to be my next bracket. My next bracket is going to be between 3, which is this is negative, and this is positive. So I can immediately actually say that I basically bypass these 2 roots.
So you have to look at the graph and analyze it.
Yes. And that's what method is going to do. It's going to take the middle point, evaluate what is the next. Yes? So you still find a root, you just didn't find them all. So in practice, what you actually do, you have to actually have some sort of a bracket search, if you will, going in over the range of reasonable values and kind of find all of the intervals where you might have a root. Okay? And it's not an easy one because like here they're actually reasonably spaced. You might have some sort of something going like this, right? And finding all of them might be a problem, right? So it really depends on how your function behaves, what the ultimate result will be. But you actually just go on a search. You go and test different intervals and you see where it is that you might have a root. Yeah? All right. Okay. Now let's move on to a different method. So part of the problem with bisection is that it has certain pace of how it's executed. Every time I go, I will get a twice smaller interval, and I keep going. That sounds like pretty good, except that often when I'm executing something a million times in a go, whether I take 20 or 100 steps to get there versus 5 matters a lot. And in a reservoir simulator, yes, you are going to look for roots a million times easily. Okay? So in that sense, we need to speed up. So one thing that is specific for bisection, I never really looked at the values of function much because they don't determine how large is my interval. It kind of just determines which part of the interval I go with. So there is now an attempt to be a little greedier. Say, hey, let's look at the approximation of this function. So I have some nonlinear function. Okay, this here is in blue. And let's look at, and this is my bracket. I have a negative value times a positive value, so I should have a root in between. Unless I have some weird function like tangent, has those points where it blows up because cosine of x is 0, right? So at those points you might have something like, woo, right? So that aside, if I have a normal, that's what I mean by a continuous function on this interval, I'm going to have a root somewhere in between. So here I'm going to say, hey, if I approximate this function with a line, that's a crude approximation, but it sometimes works, then I can look at the 0 of that. Okay? And I can hope to be closer to this root than a midpoint would be. That's a good guess. Sometimes it works, sometimes it doesn't. Okay? So in that sense, I'm just going to say, hey, my XR, and this is a simple geometry problem to figure out because these two triangles are similar. Therefore, this relates to this, the way this relates to this, right? So I can easily set up and find what my XR would be from those relationships. I just have to be, in this geometry problem, have to be a little bit careful to keep positive values, okay? So basically my f of xl, which is this length here, let me show so it's on a video. So this length is this, okay? And that's negative in this case, divided by xr minus xl, okay, is f of xu, which is positive in this case. So I'm going to take this xr minus xu, which is negative. So I have two negative values, but in terms of absolute values, these relationships should hold through. So I can just calculate what the xr is. Okay? And I'm going to calculate it for you. This is what it is. It's a little bit of algebra. And now I'm going to just say, I'm going to hope that this is going to be a smarter choice for, instead of a midpoint, which is always in the middle, I'm hoping to be closer. And then I'm going to, again, just look at the left side versus right side, okay, and see which of these brackets works better and proceed just like I did with bisection. So you have a code for bisection. Let's use the code from the last time from Monday and just modify it and call it FalsePosition. So take the code, so I'm going to literally do this entire code, cut, copy, and paste. What I just did is the best part. You make the best code when you actually reuse it in some way. So this bisection code has worked fine already. We will just now modify it and call it FalsePosition. So why don't you all modify it? To work like this. and then execute for some previous choice. So for now, ignore this, just modify the code and get a working code for false position method. And if you got it right, it should be what, 14.76 or 78 or somewhere there for that parachutist problem. And unless anyone has if anyone has questioning, you is up there, can help out. And meanwhile, I'll do the same on my code. I'm just not going to project necessarily. Do you all have copies of the slides, or did I just remove you the formula you need?
Well, I wrote it down.
Good. Did everybody else write it down? Did everybody get there? No? You type in?
I'm not sure how to, I'm not having that started. I'm not sure how to use
So this, yes. Let me now project this stuff. Type it in. So formula is back. So this is your XR instead of that midpoint. Type in that.
And everything else is same.
And everything else actually that the algorithm. So that's the point of reusing the code. Now there is some space for typos here, but those are avoidable errors in computing. Also known as little bugs. So now, for those of you who are done, how would you figure out which one is better, bisection or false position? What would mean better?
You count the number of iterations.
Yes, so do that. So in both functions, add a little counter how many iterations it took. And again, it might not turn out that for this particular problem, false position is better, but where would I do that? I would say, hey, iteration is, I'm gonna call this starting one iteration 1. Oops, no, before the loop. So I'm just going to actually increment the number of iteration every time I'm in the loop. And before I return from the function, I can just say print number of iterations is, and this number of iterations. Okay. And I'm just going to return this guess of XR. It's up to me. I can actually return the number of iterations as well if I wanted to. That's part of the design of your function, but I'm not going to bother this very moment. You might need to bother for your homework. And let me do the same for this one. So iteration is iteration plus one. Okay. So I'm going to save, execute this both cells. So let's now, when I try a false position between 12 and 16, or whatever other bracket you'd like to test, I will get 17 for false position and 13 for bisection. So I actually contradicted myself on this problem. So false position didn't give me any better result. It actually is slightly worse. And that kind of depends on how a nonlinear function is nearby this problem. Questions? So again, the key is that I basically reuse the code. I just defined this point where I'm splitting the interval differently. I tried to be smart by looking at the linearized version of the function, just a straight line between the two. Questions? Did everybody get this? So number of iterations is one way. I might also want to, if you want to get closer, so there's something that I built in here, so this is just to comment a little more on the design of the function. Here I silently built 0.001 as I'm good and I'm close enough. I could, in both of these functions, actually improve my design and set it to input epsilon, and then use this as an epsilon. So we could do that, something like this. Okay? But then I actually have to call that function with an epsilon. And then I would still get the, well, I wouldn't get the same result. Oh, one thing that I forget is to execute the cell before. There we go. Or I could actually give it a default value. And if I give it a default value, if I don't specify anything, it's going to take that default value. Does it make sense? That's kind of really neat. If you want to modify it, but if not, it's going to work just fine. And that is, again, a very good design of functions. See, it executes just the same. I didn't give it epsilon, but it took it as 0.001 because I didn't provide anything. Okay? So those are certain flexible things that you basically design as you write the code. Great. So we decided for this particular problem, false position didn't give me faster convergence. But often, actually, in a lot of problems, when a function is a little more nonlinear than this one, you will find something like this. You can also find the relative error. How would we find relative error?
true value minus approximation over true value.
Great definition. What is a true value in this problem if I'm looking for it? We don't know it, right?
Right.
So you would take the last two iterations. And in these intervals, these bracketed methods, you would just take that bracket because that's basically your approximation of the root, the endpoints of this interval. So you would just take and you would divide it by one of the ends. So there's a little bit of there like open for interpretation. What do you take as your true value? You could just take xu minus xl divided by either xu or xl. Okay. You could also work with xr as a true value. Those are all choices. Ultimately, really, the method converges or it doesn't, it does so fast or not, and this small definition of whether you took xr or xl or xu as your actual root, in all cases, you're within the epsilon that you gave, and that's all you can say. So there are some little bit of choice there, but it doesn't make a huge difference. So you can compute relative error, and if you were plotting the relative error, you would actually see something like this for a lot of problems for false position. All right, so here is an example where false position is really bad. And that is an example of a function that starts off really slowly and then speeds up. It's x to the 10 minus 1. And then basically what the problem is that when you do linearization of this function, you're really far away from the function itself, as far as you could be. So this intersection is really far away from the actual root. And in essence, your false position is attempting to be smart, but it's not really smart. Okay? So it's not going to always work, and this is part of this. You have to try it out for the problem you have, and then implement the best one out there. All right. So this is, in summary, we have bracketing methods for finding roots. You kind of graphically figure out where this root might be, and then you find yourself a bracket around the root. And basically either bisection method or false position method gives you a strategic way to get closer and closer to a value that you can use in further calculations. And which one works better? So basically false position is attempting to be faster by approximating function with a linear approximation. If that approximation is not good, then it's not going to work well. Okay? So that's essentially the case. Now, this business of finding a bracket is annoying, and I'd like to let go of that. I'd like to just give it, hey, start with 0, go. So now our next will be actually attempt to create methods that work like that. They start from one value and then just find the result. Those are so-called open methods. So they require one starting guess, and they're usually faster. Nothing. There's no free lunch in root finding methods. They are faster if they work, except that a lot of times they don't work. So you have to be reasonably close to the root. And that seems to be the theme of root finding methods. You have to be reasonably close. You either have a bracket or you have a starting point that is relatively close. So let's give it a try. Here's one that is conceptually really simple. It's called a fixed point iteration. It says, okay, so let's say that I have an example. I'm looking for the roots of x squared plus x minus 1. I arrange that algebraically into something that says x equals to the rest of it. Okay? So in this case, I'm not actually working with f of x is equal to 0. I rearrange my f of x is equal to 0 to something that looks like x equals to, I'm going to call it g of x. Okay? So now I have this x, and then this is g of x. And now just in terms of like attempting to work and find something, it's appealing to just start with a value, x1, x0, however you want to call the starting value. And then your next iteration is g of x0. And the next iteration, so call that x1, is g of x1. And you just keep going, reevaluating G of. That's, if it works, that'd be great. It's kind of simple to implement, right? So why would that kind of work? Let's see an example. So let's see that I have here a function. So I have this g of x. It's right here. And this is a graph of g of x. And I have x. Okay? So I'm looking for intersection of the two. Okay? So I start with the value. Here is my x0. And I evaluate g of x0. Boom, right here. So this point here is x0, g of x0. If I walk myself over using the constant y value, g of x0, here, when I meet y is equal to x, this is going to be precisely my g of x0, because this is where both of them are equal. Okay? So this is my x1, I'm going to call x1, that's g of x0. Now I use that value and I repeat. So I find g of x1, I walk over to function y is equal to x, and that's my x2. And it appears that this function is well suited for this because I'm gonna kind of just roll into my solution. Great. So in this case it works. Where it really works is when I have a relatively mildly sloped g of x. If I have something that is very steep, it ain't gonna work. So this example here, if I evaluate here, this is x0, g of x0, then I walk over to this function, then I get larger and I kind of spiral away from my intersection. So when I have a violently changing g of x, it's g prime, its slope is large, ain't gonna work. Right. And for negative values, I could repeat the similar process. In negative values, I'm going to go back and forth, but I can either zoom into my root or spiral away from it. Okay? So basically, this will work when I found this g of x such that g prime, its slope is mild, and that mild has to be numerically less than 1. If I find such problem, then it's not going to be a problem. Now, does that have to be over the entire interval? No, really close to that root, g prime of x should be less than 0. Okay? Otherwise, I'll diverge. Okay? So let's just give this a shot. Let's do this b example, x to the 4 minus x minus 10. And first, before we start programming, can you come up with 2 or 3 different ways to do this fixed point iteration? So using f of x is equal to x to the 4 minus x minus 10. So take a piece of paper, write down one, and let's see as a group if we can come up with more than one. So again, you have to formulate this or move things around so that you have x equals to something else. But that it's still, you didn't go away from this f of x is equal to 0. So you can move things to the right, to the left. You can divide by things and transform the equation so that whatever solves x is g of x also solves f of x is equal to 0. And if you came up with something, you were very welcome to program it and test if it works. So I could go and analyze analytically whether it works and use my calculus skills, or I can just go test it. That's an option in numerical methods. What's the first? Can somebody offer a first version you came up with? Yes. So x equals to x to the 4 minus 10 is the easiest one. Another one, what would be another one? And I can tell you immediately that one is not going to converge because it's easy. So let's try it harder. What's another version? Go ahead.
X equals 1 x squared plus 10 x cubed.
X equals 1.
1 x squared plus 10 on x cubed.
What is 1 on x squared?
I just divided every term by x cubed.
Ah, okay. Okay. 1 over. Okay. So what is 1 on? All right. So he basically put x to the 4 on one end equals to x plus 10 on the other, and then just divide everything by x cubed. Okay? That's a version. I think that should work. You can give it a try. Another thing is actually just to take 4th root. So it's x plus 10 to the 1 over 4. Anybody came up with anything else? So here are 2 examples, and then this one I'm going to type in. So these are my 3 options. So third one is x equals to x plus 10 and essentially divided by x cubed. Yes? So all of these are options. Question is which one will converge. For the first one, so we can actually program this starting value x0 is equal to 0. We don't have the time to do that. So I'm going to task you to basically start with x0 is equal to 0 and develop a simple iteration that will keep going and assign new x as x is equal to g of x, whichever of these choices for g you'd like or you came up with. And maybe it converges, maybe it doesn't. Just give it a try. And we're going to do that for Friday, and then we're going to analyze on Friday a little further. So basically, just to give you a hint, you're going to start with x0 is equal to 0. You're going to define your g of x as one of these functions. So the first one would be return x to the 4 minus 10. Okay? And then you will have an iteration here. And that iteration, of course, has to stop when your new value of x and all value of x are close enough. So we will still, again, have that epsilon business in there. And you just keep producing new values and see whether you get anywhere. Okay? And we will continue on Friday.
Es que